Right now, a machine drifting 1.5 million kilometers from Earth is quietly rewriting everything we thought we knew about the universe. What it found should not exist, and yet it does, everywhere Webb looks. Today we uncover what the James Webb Space Telescope actually discovered and why it changes everything. Now let's go. In the summer of 2022, the James Webb Space Telescope sent back its first images. Within 48 hours at least, 5 of the world's leading cosmologists used the same word to describe what they saw: broken. Not the telescope, the model of the universe itself. What Webb found was a galaxy called GLASS, Z13. It existed when the universe was only 300 million years old, and it already contained billions of stars. According to every calculation made in the previous 3 decades, this was not supposed to be possible. To understand why that single discovery sent shockwaves through the scientific community, consider what building a galaxy actually requires. Gravity must first pull hydrogen gas together across vast distances. That gas must cool slowly, collapse inward, and ignite into stars. Those stars must live out their full lives, exhaust their fuel, and die in violent explosions that scatter their material back into space. A next generation of stars then forms from that enriched debris, and the entire process repeats over and over across hundreds of millions to billions of years. Each step depends entirely on the one before it. There are no shortcuts. There is no way to skip ahead. GLASS Z13 appeared to have skipped most of those steps entirely. But that was only the beginning. Webb was not finding 1 or 2 unusual objects that could be dismissed as rare exceptions or explained away by measurement error. It was finding this same pattern again and again in entirely different regions of the sky, confirmed across multiple instruments, cross-checked by independent research teams working separately from one another. Galaxy after galaxy, all appearing far too large, far too bright, and far too structured for the age of the universe at the time they existed. The scientific community's response was not excitement. It was something closer to controlled disbelief. Independent research groups spent months checking and rechecking the data before publishing their findings because the implications were serious enough that no one wanted to be wrong. The observations were verified. The pattern held. This mattered because the Lambda CDM model, the theoretical backbone of cosmology for over 30 years, was built on a specific and carefully tested assumption. The early universe was sparse, fragile, and slow. Structure took time. Large galaxies required billions of years to assemble through countless mergers and gradual accumulation of material. The cosmic dawn was expected to be dim, quiet, and just barely beginning to stir. What Webb was showing quietly and consistently was that the early universe was none of those things. Then came the detail that made the problem significantly harder to explain away. Deep inside the light spectra Webb collected from several of these ancient galaxies, scientists found carbon and oxygen, 2 elements that seem ordinary enough in everyday life, but whose presence in galaxies only 500 million years old is deeply significant. Neither of these elements existed right after the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium. That was all. Carbon and oxygen can only be forged inside the cores of stars, where temperatures and pressures are extreme enough to fuse lighter elements into heavier ones. And crucially, those elements only get released into the surrounding space when a star dies, most often in a supernova explosion of extraordinary violence. Their presence in galaxies, just 500 million years old, meant something that was difficult to absorb at first. Before the galaxies Webb was currently observing had even fully assembled, an entire previous generation of stars had already been born, had lived out their complete lives, and had died. Not just a few stars. Enough stars to enrich the surrounding gas with detectable quantities of carbon and oxygen across entire galaxies. An entire stellar generation, complete, gone, before the universe had reached its 500th million year. The timeline that astronomers had spent decades carefully constructing was compressing in ways the standard model had no comfortable explanation for. Some researchers began describing the situation as a genuine crisis in cosmology. Others were more measured in their language, noting that the field was still gathering data and that revising a model is a normal part of science. But the data kept returning the same result. The early universe had been far more active, far more structured, and far more chemically evolved than anyone had predicted. Something had happened in those first few 100 million years that current theory does not fully account for. And whatever it was, it left behind galaxies that by every established rule should not have been there. If a complete generation of stars had already managed to form, live and die before the universe was 500 million years old, then what happened during those first 300 million years that we know almost nothing about? To understand why those galaxies should not exist, it helps to understand how Webb is able to see them at all. And the way it does that turns out to be stranger, in its own quiet way, than anything it has discovered so far. Webb is not a telescope in the way most people picture a telescope. If you placed your eye against its instruments and looked, you would see nothing at all. Complete darkness. Because Webb observes the universe entirely in infrared light, a range of wavelengths that sits beyond what human eyes can detect. This is not a limitation of the design. It is the entire reason the instrument was built the way it was. Light travels at a fixed speed of roughly 300,000 kilometers per second. That speed is constant across the entire universe, and nothing moves faster. At human scales, that feels essentially instantaneous. Light crosses a room before any nerve in your body could register the delay. But the universe operates on scales that make human intuition completely unreliable. The moon you see in the sky tonight is not the moon as it exists right now. It is the moon as it was 1.3 seconds ago, which is how long its light took to reach you. The sun you see each morning left its surface 8 minutes before your eyes received it. If the sun were to vanish completely at this exact moment, the sky would remain bright for 8 more minutes before darkness arrived. The nearest star beyond our sun, Proxima Centauri, appears to us as it was more than 4 years in the past. In the universe, distance and time are not separate things. They are the same thing measured in different units. When Webb looks at a galaxy 13 billion light-years away, it is not simply looking far. It is looking 13 billion years into the past. That galaxy, as it exists today, wherever it is and whatever it has become, is completely unknown to us and will remain so permanently. What we receive is a message sent across an almost incomprehensible span of time, arriving now only because it began its journey so long ago. This is what makes Webb, in a precise physical sense, and not merely a poetic one, a time machine. But there is a complication, a fundamental one built into the nature of the universe itself. The universe has been expanding continuously since the moment of the Big Bang, and that expansion does something to light that fundamentally changes it during the journey. As light travels through space, and space itself stretches, the wavelength of that light gets stretched along with it. A photon that began its journey as visible blue light gradually shifts toward red as it travels. Over billions of years of travel through an expanding universe, that stretching becomes extreme. Light that originally shone in wavelengths visible to the human eye gets pulled far beyond the visible spectrum, entirely shifting into infrared wavelengths by the time it finally arrives. This is why the earliest galaxies in the universe were invisible to Hubble. Not because Hubble lacked power or precision. Hubble was an extraordinary instrument, but it was designed to observe visible light and near infrared. The most ancient light in the universe, by the time it reaches us, has shifted far beyond that range. Those galaxies were always there. Their light had simply moved beyond the limits of what Hubble was built to see. Webb was designed from the beginning to follow that light into the infrared. Its primary mirror stretches 6.5 meters across and is coated in a microscopically thin layer of gold, chosen because gold reflects infrared wavelengths with exceptional efficiency. The mirror is divided into 18 hexagonal segments, each one polished to a precision measured in nanometers. In space, all 18 segments were carefully aligned to work as a single unified surface, a process that took months of calibration after launch. Then there is the problem that makes the entire engineering challenge genuinely extraordinary. Infrared light is intimately connected to heat. Every warm object emits infrared radiation. The human body emits it. The electronics inside a spacecraft emit it. Even the mirror itself, if it were anywhere near room temperature, would glow in exactly the wavelengths Webb is trying to detect, drowning out signals that have been traveling for billions of years under a flood of thermal noise from the instrument itself. To solve this, Webb must be kept extraordinarily cold. A 5-layer sunshield, roughly the size of a tennis court, sits between the telescope and the sun, blocking the heat and light from the sun, the Earth, and the Moon simultaneously. On the shadowed side of that shield, the telescope cools to around -233 degrees Celsius. At that temperature, Webb becomes quiet enough to detect light so faint it arrives as individual photons, one by one, from galaxies that formed when the universe was still in its infancy. The telescope operates 1.5 million kilometers from Earth at a gravitational balance point known as Lagrange point 2, where the combined gravity of the Earth and Sun keeps it locked in a stable position without constant fuel expenditure. From that remote location, shielded from interference and cooled to near absolute zero, Webb stares into regions of sky that appear completely empty and waits, sometimes for hours, sometimes for days, collecting ancient photons one by one until a picture slowly assembles itself from the darkness. There is something worth pausing on here. When Webb photographs the earliest periods of cosmic history, it is technically capturing images of events that occurred before the Earth existed, before the Sun existed, before the Milky Way had taken anything close to its current shape. Webb possesses a collection of images from an era before cameras, before planets, before stars like ours were even born. That is, by any reasonable measure, the strangest photo album in the history of anything. The night sky itself carries this same quality, though we rarely think of it that way. The brightest star you might see on a clear night could have exploded 1,000 years ago, and the light from that explosion has not reached us yet. You are looking at the ghost of something that no longer exists, without any way of knowing it. Every point of light in the sky is a message from a different moment in the past, all arriving simultaneously, layered together into a single image your brain interprets as the present. The night sky is not a view of the universe as it is. It is a mosaic assembled from millions of different moments in history displayed all at once. If there is a civilization 65 million light-years away looking toward Earth right now, their telescope is currently observing dinosaurs, not human beings. So, is there a civilization out there somewhere observing us at this very moment? Webb looks 13 billion years into the past and finds galaxies that should not exist. But 13 billion years is not the boundary of the universe. It is only the boundary of what we can currently see. The universe is actually far larger than that figure suggests, and in a way that makes even the most basic mathematics appear at first glance to have simply stopped working. Here is a contradiction that stops most people cold the first time they encounter it. The universe is 13.8 billion years old. Light travels at a fixed speed. Nothing moves faster than light. So the farthest anything could possibly be from us is 13.8 billion light-years, because that is the maximum distance light could have covered since the beginning of everything. The observable universe has a radius of 46 billion light-years. Those two statements cannot both be true, and yet they are. This is not a rounding error. It is not a simplification made for public communication. It is what the measurements actually show, and it follows directly from one of the most counterintuitive properties of the universe. Space itself is not bound by the speed of light. The cosmic speed limit applies to matter and information moving through space. A spaceship cannot accelerate past the speed of light. A signal cannot travel faster than light from one point to another. Those rules are absolute and have been tested to extraordinary precision. But they say nothing about the behavior of space itself. Space is not a thing moving through something else. It is the fabric within which everything moves, and that fabric can stretch at any rate without violating any law of physics. This distinction sounds abstract until you follow it to its conclusion. When a distant galaxy emitted the light that Webb is now detecting, that galaxy was much closer to us than it is today. the light began its journey across a relatively smaller gap. But during the billions of years that light spent traveling toward Earth, the universe continued expanding. Space between us and that galaxy kept stretching continuously for the entire duration of the journey. The galaxy was being carried farther away even as its light was moving toward us. Think of an ant walking along a rubber band that is being slowly stretched between two hands. The ant keeps moving forward at a steady pace, making genuine progress. But the far end of the rubber band keeps getting pulled away. If the rubber band stretches slowly enough, the ant eventually reaches its destination. If it stretches too fast, the ant never arrives, regardless of how long it walks. Light crossing the universe faces exactly this situation. The light is the ant. The expanding universe is the rubber band being pulled apart. This is why a galaxy whose light has been traveling for 13 billion years can now be located 46 billion light-years away. During those 13 billion years of travel, the space between us and that galaxy expanded dramatically. By the time the light arrived, its source had been carried far beyond the distance the light itself had covered. The observable universe then is a sphere with a radius of 46 billion light-years, not because anything traveled that far in 13.8 billion years, but because the space those ancient photons crossed has been continuously expanding throughout the entire journey. At the edge of this observable sphere sits something called the cosmic horizon. It is important to understand what this boundary actually is, because it is easy to imagine it wrongly. It is not a wall. It is not a physical edge where space stops or matter runs out. It is a boundary of information. Beyond it, the universe continues to exist. Galaxies form and evolve, stars ignite and die. Structures grow under gravity exactly as they do in the regions we can observe. But light from those regions cannot reach us, because the space between us and them is expanding faster than light can cross it. No signal from beyond that horizon will ever arrive here. Not because of any technological limitation, because the physics of an accelerating expansion makes the journey permanently impossible. This means that most of the universe is hidden from us forever, not temporarily while we wait for better instruments, permanently as a fundamental consequence of how the universe works. No telescope that could ever be built, no matter how large or sensitive, can show us what lies beyond that horizon. The information simply does not exist here, and never will. There is something deeply strange about what this implies for the idea of a center. Every point in the universe sits at the center of its own observable sphere. From any given location, space extends equally in all directions out to its own cosmic horizon. An observer in a galaxy billions of light-years away has an entirely different observable universe than we do, with regions visible to them that are permanently hidden from us, and regions visible to us that are beyond their horizon. Entirely. There is no special viewpoint from which the whole cosmos can be seen. There is no location that could claim to be the true center. If every point in the universe is the center of its own observable region, then where is the actual center of the universe? 93 billion light-years across sounds staggering. It is, but that is only the portion of the universe we can observe. How much larger is the universe that actually exists beyond that boundary? The answer from modern physics will make 93 billion light-years look like a grain of sand. The observable universe spans 93 billion light-years from one side to the other. That number is real, measured, and as precise as current instruments allow. But it is critical to understand what it actually represents. It is our observational bubble, the region from which light has had enough time to reach us. It says nothing whatsoever about where the universe ends, because there is substantial evidence that the universe does not end. The first line of evidence comes from the cosmic microwave background, the faint glow of radiation left over from roughly 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. That radiation has been mapped across the entire sky in extraordinary detail, and what those maps show is uniformity. In every direction, in every patch of sky, the cosmic microwave background looks essentially identical. Its temperature varies by only tiny fractions of a degree from one region to the next. There is no direction in which it appears to thin out, fade, or show any sign of approaching an edge. If the universe had a boundary anywhere near our cosmic horizon, the structure of that radiation would reflect it. It does not. The second line of evidence is geometric. If the universe is finite and curved, like the surface of an enormous sphere, then light traveling in a straight line long enough would eventually return to its starting point. The geometry of such a universe would leave measurable signatures in the pattern of the cosmic microwave background. Every careful measurement made to date shows the universe to be geometrically flat to a precision of 0.4%, not curved, not closed. Flat within the limits of what current instruments can detect. A flat universe can be finite, but the measurements place any possible boundary so far beyond our observable horizon that it becomes effectively indistinguishable from infinite. The universe may be truly infinite in extent, or it may be so large that the difference is physically meaningless. But the most striking argument for just how vast the universe beyond our horizon might be comes from understanding what happened in the very first moments after the Big Bang. In the first fraction of a second, something remarkable occurred. The universe underwent a period of extraordinarily rapid expansion called inflation. During a window of time so brief, it is almost impossible to express in ordinary terms, lasting perhaps 10 to the power of negative 32 seconds, the universe expanded by a factor that dwarfs any number with a practical name. Regions that were in contact with each other close enough for heat and information to be exchanged were suddenly pushed so far apart that light could no longer travel between them. What had been a tiny, causally connected region became a vast, smooth, nearly uniform expanse. The universe we can observe today grew from what was before inflation, an almost incomprehensibly small patch of that original space. Everything outside that original patch was inflated outward, beyond our horizon, before the universe was even a fraction of a second old. It has been there ever since, utterly inaccessible, expanding away from us faster than any signal could ever cross the gap. The consequence of this is almost impossible to hold in the mind. Current estimates suggest the total universe may be larger than the observable universe by a factor of at least 10 to the power of 23. That is a 1 followed by 23 zeros. There is no analogy that makes this number feel real. Saying the observable universe is to the total universe, as a single atom is to the observable universe, actually understates the ratio. The number is simply beyond the reach of intuition entirely. Webb's role in all of this is to map what we can see with the highest precision ever achieved. By detecting galaxies at the very edge of the observable universe and measuring how they are distributed across vast scales, Webb provides the data that theorists use to test and refine models of inflation of cosmic geometry and of what the prover-sozing universe beyond our horizon might look like. Every precise measurement Webb makes tightens the constraints on those models, ruling out possibilities and narrowing the range of what the evidence can support. What those measurements consistently show is a universe that gives no hint of ending anywhere near the limits of our vision. The density of galaxies does not thin toward an edge. The cosmic microwave background shows no boundary. The geometry shows no curvature that would suggest a closed, finite space. Everything points in the same direction. The universe is vastly, perhaps infinitely larger than the portion we will ever be able to observe. And within our observable bubble, the distribution of all that matter is not random. It is not a uniform fog of evenly spread galaxies drifting through space without pattern or structure. It is organized. Intricately, magnificently organized into a pattern so large and so complex that it was not even confirmed by direct observation until Webb began mapping it in detail. If the universe is truly infinite, then by pure probability somewhere out there in that infinity there is an exact copy of you reading this sentence right now. How does that make you feel? The universe may be infinite, but inside the 93 billion light-year region we can observe, matter is not distributed randomly. It forms a structure, the greatest architecture that has ever existed, and Webb has just mapped it in greater detail than ever before. Step back far enough from the universe, and the galaxies stop looking like scattered points of light. They form threads, enormous sweeping filaments stretching across hundreds of millions of light-years, connecting clusters of galaxies at their intersections like knots in a vast net. Between those threads lie regions of space that are by any practical definition empty, not sparse, not thinly populated, empty in a way that is genuinely difficult to comprehend. No galaxies, no star clusters, almost nothing at all across distances that dwarf the entire observable neighborhood of the Milky Way. This is the large-scale structure of the universe. Astronomers call it the cosmic web. And for a long time it existed primarily as a prediction, something that computer simulations produced consistently, but that direct observation could only partially confirm. Webb changed that. Webb is now observing what are called protofilaments, the earliest versions of these cosmic threads forming when the universe was only a few billion years old. These structures were not supposed to be so well developed that early. The fact that Webb can see them taking shape already, organizing into the pattern that would eventually become the web we observe today, is another entry in the growing list of things the early universe did ahead of schedule. The cosmic web did not slowly emerge over the full age of the universe. It began assembling itself much earlier than the models expected. What makes the web so striking when you first see a map of it is not just its scale, it is how familiar the pattern looks. The long filaments, the dense nodes where they intersect the sprawling voids between them. The overall structure bears a remarkable resemblance to something far smaller and far more intimate. The network of neurons in a human brain with its branching connections and densely linked hubs follows a pattern that looks to an unsettling degree like the large-scale structure of the universe. This resemblance is not coincidence in the mystical sense, and it is not an illusion produced by pattern-seeking minds. It has a mathematical basis. Both structures, separated by a factor of roughly 27 orders of magnitude in scale, follow the same underlying principles governing how complex networks organize themselves. When many nodes each form connections preferentially with other well-connected nodes, and when growth is governed by local rules rather than central planning, the result tends toward this kind of filamentary clustered architecture. The universe and the brain arrived at similar-looking structures not because they are secretly the same thing, but because the mathematics of network formation under certain conditions produces this kind of pattern, regardless of what the nodes actually are. The universe and a human brain are made of entirely different things and governed by entirely different forces, but they solved a similar organizational problem in a similar way. Now consider the opposite of those dense, glowing filaments. The Bootes void is a region of space discovered in 1981, located roughly 700 million light-years from Earth. It spans approximately 330 million light-years across. Inside it, there are almost no galaxies. A handful have been found near its boundaries, but the interior is nearly bare. If the Milky Way happened to be located somewhere near the center of the Bootes void, rather than where it actually is, the nearest neighboring galaxy would be so distant that even the most powerful telescopes available today would struggle to detect it. The night sky would be essentially dark. There would be no evidence that other galaxies existed. An entire civilization living inside that void might spend thousands of years developing astronomy and ultimately conclude with apparently solid evidence that the universe contained exactly one galaxy and nothing else. The Bootes void is not unique. The universe contains many such regions distributed across the spaces between the filaments of the cosmic web. Some are smaller, some comparable in scale. Together, they make up the majority of the universe's volume. The cosmic web, for all its visual impressiveness, is actually a relatively thin scaffold stretched across an enormous amount of emptiness, which raises the obvious question: what built this scaffold? The visible matter in the universe, the gas, the stars, the galaxies themselves, did not have enough mass to spontaneously organize into structures like this on its own. Calculations performed decades ago showed that if only ordinary matter were present in the early universe, the gravitational fluctuations that seeded galaxy formation would have been too weak to produce the structures we observe today. Something else had to be there first, providing a deeper gravitational framework that visible matter could fall into. That something makes up 85% of all the matter in the universe. It does not emit light. It does not reflect light. It does not interact with electromagnetic radiation in any way that any instrument has yet been able to detect. It has never been directly observed. Its existence is inferred entirely from its gravitational effects on the things we can see, and those effects are unmistakable and consistent across every scale on which astronomers have looked. This invisible material formed the earliest structures in the universe, pulling together into vast halos long before ordinary matter had cooled enough to collapse. The filaments of the cosmic web trace the skeleton of those invisible halos, with visible galaxies appearing where the halos were dense enough to trap gas and ignite stars. The glowing threads and bright clusters that Webb maps so beautifully are in a real sense just the lit portions of a much larger invisible architecture. The cosmic web we can see is the surface of something we cannot. Our own galaxy participates in this structure in a way that very few people are aware of in their daily lives. The Milky Way is located on a filament of the cosmic web and is currently moving along with the local group of galaxies and a vast surrounding region of space toward an immense gravitational concentration. This region, known as the Great Attractor, sits roughly 250 million light-years away in the direction of the Centaurus and Hydra constellations. The entire local neighborhood of galaxies, including everything within roughly 100 million light-years of us, is being drawn toward it. The Milky Way is moving in that direction at roughly 600 kilometers per second, not 600 kilometers per hour, per second. That motion is happening right now, continuously, as you read this. It was happening yesterday. It has been happening for billions of years. At no point does it register in any way in daily human experience. The scales involved are simply too vast for the speed to feel like anything at all. 600 kilometers per second through a structure 250 million light-years wide is in practical terms barely adrift. This is the nature of existence inside the cosmic web. Motions that would be catastrophic at human scales are geological in their slowness at cosmic ones. The Milky Way is rushing toward the Great Attractor at 600 kilometers per second. What is pulling our entire region of the universe in that direction? The thing that built the cosmic web, the thing that keeps galaxies from flying apart, and the thing that is pulling the Milky Way toward the Great Attractor makes up 85% of all matter in the universe, but has never been seen even once, and its story is stranger than anything in Act 1. Everything you have ever seen, touched, or measured belongs to the same category. Your body, the chair beneath you, the air in the room, every star visible on a clear night, every galaxy Webb has ever photographed, every planet, every moon, every cloud of gas drifting between star systems, every atom of every element on the periodic table, all of it combined accounts for roughly 15% of the matter in the universe. The other 85% is something physics cannot currently explain. This is not a gap in the data that will be filled by a missing decimal place. It is not a provisional estimate waiting to be corrected. It is one of the most rigorously tested and consistently confirmed results in all of modern science. The universe contains vastly more mass than everything we can see, detect, or interact with. And despite nearly a century of increasingly sophisticated investigation, no one has ever directly observed what that mass actually is. The first serious evidence appeared not from a grand experiment, but from a careful observation that quietly refused to make sense. When astronomers mapped the rotation of spiral galaxies, they expected to find a straightforward pattern. Stars close to the galactic center, where most of the visible mass is concentrated, should orbit quickly. Stars in the outer regions, far from the bulk of the mass, should orbit much more slowly, just as the outer planets of our solar system move more slowly than the inner ones. This relationship between distance and orbital speed is a direct consequence of gravity tested and confirmed across centuries of observation within our own solar system. What the measurements showed instead was that stars in the outer regions of spiral galaxies were orbiting at roughly the same speed as stars much closer to the center. In some cases, the rotation curve was almost completely flat from the inner regions all the way out to the visible edge of the galaxy. This meant that the gravitational force acting on those outer stars was far stronger than the visible mass of the galaxy could produce. If only the stars, gas and dust that telescopes could detect were present, those outer stars would not be in orbit at all. The centripetal force required to keep them on their circular paths simply would not exist. They would have drifted away into intergalactic space billions of years ago. Something invisible was providing the additional gravity. Something distributed not just through the visible disk of the galaxy, but in an enormous spherical halo, extending far beyond the visible boundaries, wrapping each galaxy in an unseen shell of mass, many times larger than the galaxy itself. The second line of evidence came from a collision. The bullet cluster is the result of two massive galaxy clusters passing through each other at high speed. When they collided, the ordinary matter in each cluster behaved as ordinary matter does. Gas clouds slammed into each other, heated dramatically, and slowed down, glowing in X-ray wavelengths that made them clearly visible. The ordinary matter was caught in the collision, compressed and heated, lagging behind the galaxies themselves. But gravitational lensing maps of the region told a different story. By measuring how the light from background galaxies was being bent and distorted by the mass of the bullet cluster, astronomers could reconstruct where the mass was actually located. And the mass was not where the hot, glowing gas was. The majority of the mass had passed straight through the collision without slowing down at all, as if the two clusters were nearly transparent to each other. It had separated cleanly from the ordinary matter and continued moving undisturbed. This behavior is exactly what you would expect from a type of matter that interacts gravitationally but barely interacts with itself or with ordinary matter through any other force. The bullet cluster did not prove dark matter exists through an indirect chain of reasoning. It showed directly and visually the separation of mass from visible matter during a collision. It remains one of the most compelling pieces of evidence in the entire field. The third line of evidence is written into the oldest light in the universe. The cosmic microwave background, the faint radiation released roughly 380,000 years after the Big Bang, carries within its subtle temperature variations a detailed record of what the early universe was made of. The precise pattern of those variations, the specific sizes and amplitudes of the fluctuations, can only be reproduced in theoretical models if a substantial amount of matter that does not interact with light was already present and already beginning to clump together under gravity before that. Radiation was released. Without dark matter in the equations, the models produce a cosmic microwave background that looks nothing like the one we actually observe. With dark matter included at the right proportion, the match becomes precise. 3 independent lines of evidence, from galactic rotation to colliding clusters to the structure of ancient light, all pointing to the same conclusion. The visible universe is embedded within a much larger invisible structure, and that invisible structure is what made everything else possible. Dark matter formed first. In the very early universe, while ordinary matter was still too hot and energetically coupled with radiation to collapse under gravity, dark matter was already beginning to gather. It does not interact with light, which means it was not held back by the pressure of the intense radiation field filling the early cosmos. It was free to respond to gravity alone, and it did. It pulled together into vast halos, invisible scaffolding spread across the young universe long before a single star had ignited anywhere. When ordinary matter eventually cooled enough to decouple from radiation and begin collapsing freely, it found those halos already waiting. Gas fell into the gravitational wells. Dark matter had prepared, compressed, heated, and eventually ignited. The first stars formed at the centers of dark matter concentrations. Those stars gathered into galaxies. Those galaxies connected along the dark matter filaments of the cosmic web. Every structure in the visible universe formed where dark matter had already laid the groundwork. Without it, none of this exists. Not the galaxies' Webb photographs, not the stars that forged the carbon and oxygen in your body, not Earth, not you. And despite 100 years of increasingly precise indirect evidence, and despite dozens of dedicated experiments searching for any direct signal, not a single dark matter particle has ever been detected. The underground detectors built to catch it have found nothing. The particle accelerators designed to produce it have found nothing. The space-based observatories watching for its decay or annihilation products have found nothing definitive. Dark matter may consist of undiscovered particles that interact so weakly with ordinary matter that detecting them requires instruments far beyond anything currently built, or it may point to something more fundamental, a gap in the underlying principles of physics itself. If dark matter does not interact with light or electromagnetism, is it passing through your body right now? Dark matter holds the universe together. But something else is trying to tear it apart, and not only is it winning, it is accelerating. In 1998, two research teams set out to answer what seemed like a straightforward question. Gravity pulls matter together. The Big Bang pushed everything apart. Over time, gravity should be gradually slowing that initial expansion like a ball thrown upward that slowly loses speed as it rises. The question both teams were trying to answer was not whether the expansion was slowing. Everyone assumed it was. The question was, how quickly, and whether gravity would eventually win, completely pulling everything back together in a final collapse, or whether the expansion would slow to a gentle drift and continue outward forever. To measure the deceleration, both teams used a specific type of stellar explosion called a Type Ia supernova. These events occur when a white dwarf star in a binary system accumulates enough mass from its companion to exceed a critical threshold and detonate. Because the detonation always occurs at approximately the same mass, the explosion always reaches approximately the same peak brightness. A Type Ia supernova is, in effect, a standard candle. If you know how bright something actually is and you measure how bright it appears from Earth, you can calculate precisely how far away it is. The same principle as judging the distance to a 100-watt light bulb by measuring its apparent brightness from across a dark room. By comparing those calculated distances with the measured redshifts of the host galaxies, the teams could trace how the expansion rate had changed over time. The more distant supernovae showed conditions from earlier in cosmic history. The pattern of distances and redshifts read together would reveal whether the universe had been decelerating as expected. The supernovae were too far away, not slightly, not within the range of measurement uncertainty. They were measurably, consistently more distant than any decelerating universe could account for. The expansion had not been slowing down, it had been speeding up. The universe was not losing energy to gravity. Something was actively driving the expansion faster over time. Both teams checked their calculations, then they checked them again. Then they checked the data itself, looking for systematic errors, instrument biases, or astrophysical effects that might mimic the result. They found nothing that could explain it away. When the two teams, which had been working independently and competitively, compared their results, the numbers matched. In 1998, both teams announced the same conclusion simultaneously. The expansion of the universe is accelerating. That year is, in retrospect, one of the most unsettling moments in the history of science. Because to explain an accelerating expansion, something had to be pushing it. Something had to be providing energy that was not diluting as the universe grew larger. Something that grew stronger, or at least held constant, as the volume of the universe increased. Something that was in its behavior unlike any form of energy or matter previously known to physics. Cosmologists named it dark energy. And when they calculated how much of it must be present to account for the observed acceleration, the number was staggering. Dark energy constitutes approximately 68% of the total energy content of the universe. Dark matter accounts for roughly 27%. Ordinary matter, every atom of every element, every star, every planet, every living thing, everything that 3,000 years of human science had ever studied, adds up to less than 5%. What makes dark energy particularly strange is how it behaves as space expands. Ordinary matter becomes less dense as volume increases. Pour the same amount of gas into a larger container and the concentration drops. Radiation dilutes even faster as it spreads. But dark energy does not follow this pattern. Its density appears to remain constant even as the universe grows. As space expands and new volume appears, dark energy fills that volume at the same density. The total amount of dark energy in the universe increases as the universe grows larger. This creates a feedback effect with no parallel in ordinary physics. The more the universe expands, the more dark energy exists, and the stronger the drive toward further expansion becomes. For roughly the first 9 billion years of cosmic history, matter was dense enough that gravity still dominated on large scales. The expansion continued, but gravity slowed it. Then, approximately 5 billion years ago, the matter density had dropped far enough that dark energy began to dominate. From that point forward, the expansion stopped decelerating and began accelerating instead. The universe passed a turning point, and everything since has been moving away from everything else at an ever-increasing rate. When the first teams announced their result, the immediate reaction from much of the physics community was to look for the error. The conclusion was too strange, too contrary to every reasonable expectation. Researchers spent months combing through the data, proposing alternative explanations, and searching for any systematic effect that might account for the result without requiring a new component of the universe. They found none. A second independent confirmation arrived. Then more. The result was real. It was, as one physicist later described it, one of the rare moments in the history of science when researchers genuinely hoped they had made a mistake. If dark energy continues accelerating the expansion, tens of billions of years from now, galaxies will disappear from view forever. What will that future civilization see when they look up at the sky? Dark energy is pushing the universe apart. Dark matter is pulling it together. Two invisible forces are competing, and the outcome of that competition will determine the fate of everything. But before knowing which wins, Webb has just revealed that we do not even know the precise speed of the battle itself. There are two ways to measure how fast the universe is expanding. Both are rigorous. Both have been tested, refined, and independently verified dozens of times over several decades. Both use entirely different physical phenomena, entirely different instruments, and entirely different chains of reasoning. They produce different answers, not slightly different in the way that two careful measurements of the same thing might differ by a fraction of a percent due to instrument noise. Different in a way that has survived every attempt to explain it away, grown sharper as the data improved, and now stands as one of the most significant unresolved problems in all of modern cosmology. The first method looks backward. It begins with the cosmic microwave background, the ancient radiation released roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. That radiation carries within its subtle temperature variations an extraordinarily detailed record of the physical conditions of the early universe. By analyzing the precise pattern of those fluctuations, cosmologists can extract a complete description of what the young universe was made of, how it was structured, and how fast it was expanding at that early time. From those measurements and from well-established physics governing how the universe evolves, from that point forward, they can calculate what the expansion rate should be today. The result is approximately 67 kilometers per second per megaparsec. For every megaparsec of distance between 2 points in the universe, those points are moving apart at 67 kilometers per second, and that rate scales with distance in a precise way. The second method looks at the nearby universe directly. It uses a carefully constructed ladder of distance measurements, starting with Cepheid variable stars. These are stars that pulsate with a rhythm directly linked to their intrinsic brightness, which means measuring their pulsation period reveals how luminous they truly are. Comparing that true luminosity to their apparent brightness in the sky gives their distance with high precision. Those Cepheid distances are then used to calibrate Type Ia supernovae in the same galaxies. and those supernovae visible across far greater distances extend the measurement out to where the expansion of the universe is clearly measurable. By comparing the distances to the recession velocities of those galaxies, researchers derive the current expansion rate directly from observation. That result is approximately 73 kilometers per second per megaparsec. The difference between 67 and 73 is roughly 9%. In everyday contexts, 9% sounds modest. In cosmology, where both measurements carry statistical uncertainties of only a few percent and have been checked against multiple independent data sets, 9% is a crisis. The two numbers are separated by what statisticians call more than 5 sigma, meaning the probability that the discrepancy is simply random measurement. Scatter is less than 1 in 3.5 million. Both methods are telling the truth about what they measure, and what they measure does not agree. This disagreement has a name: the Hubble tension. For years, the most optimistic interpretation was that a systematic error was hiding somewhere in one of the measurement chains. Perhaps the Cepheid calibrations were subtly wrong. Perhaps there were effects from the dust and crowded stellar environments in nearby galaxies that were skewing the distances. Perhaps the cosmic microwave background analysis was missing something. Every candidate for a systematic error was investigated carefully. Some small corrections were found and applied. The tension narrowed slightly in some analyses and widened in others. But it never went away. Then Webb entered the picture. Webb was expected to resolve the tension, or at least clarify which side of it was more reliable. Its infrared capabilities allow it to observe Cepheid variable stars with far greater precision than Hubble could, cutting through the dust and crowding effects that had been the leading candidates for systematic error on the distance. Ladder seed. When Webb measured Cepheids in nearby galaxies and recalibrated the distance ladder with its improved data, the result was unambiguous. The higher number held. The tension did not shrink. If anything, Webb's measurements made the case for the higher expansion rate more solid, not less. The optimistic explanation, the systematic error hiding in the distance measurements, became significantly harder to defend. This leaves 3 possibilities, and all of them are consequential. The first is that a systematic error still exists somewhere subtle enough to have survived every investigation so far. This cannot be ruled out, but it becomes harder to believe with each new confirmation from independent methods. The second is that something unusual about the local universe, the region within a few 100 million light-years of us, is causing the nearby expansion rate to differ from the global average. If we happen to live in a region that is slightly less dense than the cosmic average, local expansion could be slightly faster, which would make our distance ladder measurements higher than the true global rate. Some evidence for mild local underdensity exists, but not nearly enough to account for the full discrepancy. The third possibility is the one that keeps cosmologists awake at night. Something happened in the early universe that the standard model does not include. Some form of energy or physical process was present in the first few 100,000 years after the Big Bang that slightly altered the expansion history in a way that shifts the predicted rate today. Physicists have proposed various candidates for this early contribution, including what they call early dark energy, a component that would have been significant briefly and then faded. None of these proposals has been confirmed, and none fits the data perfectly. But all of them point in the same direction. The lambda CDM model, already strained by the galaxies that should not exist in the early universe, may be missing a fundamental piece. And if that missing piece turns out to be real, it almost certainly connects to the deepest unsolved problem in physics: what dark energy actually is. Every model of dark energy currently available is at its core a description of what dark energy does rather than what it is. The Hubble tension may be the first observational crack that eventually leads to an answer. If the Hubble tension is not a measurement error, but a signal of new physics, that means all of modern cosmology is missing a crucial piece. What could that piece be? The Hubble tension reveals that the current model of the universe is incomplete. But how incomplete, and what the true ending of the universe actually is, leads to the final act where physics reaches the boundary of itself. The universe has a history. It also has a future. And unlike most questions about the future, the possible endings of the universe are not speculation or philosophy. They are predictions generated by well-tested physical laws constrained by real measurements and distinguished from one another by the behavior of a single quantity, what dark energy does over time. The first scenario carries the highest probability, according to current data. It is called the Big Freeze, and it is the quietest ending imaginable. If dark energy maintains roughly constant density as the universe continues expanding, the expansion proceeds indefinitely. Galaxies that are not gravitationally bound to each other drift apart over billions of years. Eventually, the supply of cold hydrogen gas available to form new stars runs low. Star formation slows, then stops. The existing stars burn through their fuel over timescales, ranging from millions to trillions of years depending on their mass. The smallest, most frugal red dwarf stars keep burning for perhaps a few trillion years before finally going dark. After that, the universe consists primarily of cold stellar remnants, white dwarfs slowly cooling toward absolute zero neutron stars and black holes. Even the black holes eventually go. Stephen Hawking showed theoretically that black holes are not permanent. They very slowly emit radiation through a quantum process at their event horizons, gradually losing mass over inconceivably long periods. The largest black holes, the supermassive ones at the centers of galaxies, would take approximately 10 to the power of 100 years to evaporate completely. That number is so large that writing it out in full would require more digits than there are atoms in the observable universe. But eventually even they are gone. What remains is a universe at maximum entropy. A thin, cold, almost perfectly uniform distribution of the lowest energy particles across an unimaginable expanse of space. No structure, no gradients, no processes, no events. Perfect, permanent silence. The heat death of the universe brought not by fire, but by the final, irreversible victory of disorder over everything that complexity ever built. The second scenario requires dark energy to behave differently than it appears to today. If the density of dark energy is not constant, but instead increases over time, the consequences escalate dramatically. This scenario is called the Big Rip. As dark energy grows stronger, the force driving expansion begins to overwhelm gravity on progressively smaller scales. First, the large-scale filaments of the cosmic web are stretched beyond coherence. Then, individual galaxy clusters are pulled apart, their member galaxies drifting away from each other as expansion overcomes their gravitational bonds. Then, galaxies themselves are disrupted, their stars scattered. Then, individual star systems. Then, planets. The process continues down through every scale of structure. Molecular bonds break, atomic nuclei are ripped apart. In the final moments, space-time itself tears. Current estimates suggest this scenario, if dark energy is of the right type, could occur within roughly 20 billion years from now. It is the most violent of the endings and the briefest. The third scenario reverses everything. If dark energy were somehow to weaken over time and gravity eventually regained dominance on cosmic scales, the expansion would slow, halt, and reverse. Galaxies would begin moving toward each other rather than away. The universe would contract slowly at first, then with gathering speed. As everything compressed back together, temperatures would rise. Galaxy clusters would merge. Individual galaxies would merge. Stars would be pushed close enough together that the space between them glowed. Eventually, the entire observable universe would collapse back into a single incomprehensibly hot and dense point. A singularity, the mirror image of the Big Bang, but running in reverse. This is the Big Crunch. Current measurements strongly disfavor it since dark energy appears to be accelerating rather than weakening, but it cannot be formally excluded. The fourth scenario extends from the third and opens a possibility that changes the meaning of every other scenario. If the universe collapses in a big crunch, the conditions at that final singularity might not simply end. The energy and density of that collapse might trigger a new expansion, a new Big Bang, a new universe born from the death of the previous one. This is the Big Bounce. In some versions of this idea, the cycle has been repeating indefinitely, each iteration producing a universe with slightly different physical constants, different laws, different histories. The rules we consider fundamental, the strength of gravity, the mass of the electron, the speed of light, might not be fixed properties of reality, but parameters that reset with each new cycle, drawn from some broader distribution of reset possibilities. Webb is actively contributing to narrowing which of these scenarios the universe is actually heading toward. By measuring the expansion history of the universe across billions of years with unprecedented precision, and by looking specifically for any evidence that dark energy's density has changed over cosmic time rather than remaining, constant Webb's observations are slowly tightening the constraints on dark energy's behavior. Every distant galaxy, Webb measures every supernova. It captures every careful comparison of structure across different epochs, adds to the dataset that will eventually tell us whether the universe ends in silence, in violence, in collapse, or in rebirth. The answer is not yet clear, but it is within reach of current science, in a way it has never been before. Among the four ending scenarios, Big Freeze, Big Rip, Big Crunch, Big Bounce, which one do you think is the most beautiful from a cosmological perspective? Whatever scenario plays out, all four begin from the same point, the Big Bang. But what the Big Bang actually was, where it came from, and whether anything existed before it, those are the final questions, and what modern physics has to say about them will surprise you. Most people carry a mental image of the Big Bang that is almost entirely wrong. They picture an explosion. A single point of incredibly dense, hot material suspended somehow in existing space, detonating outward and flinging matter in all directions, the way a bomb scatters debris across a room. In this picture, the universe began at a specific location, expanded outward from that center, and the space it expanded into was already there, waiting to be filled. None of that is correct. And the difference between that picture and what actually happened is not a minor technical detail. It changes everything about how the event should be understood. The Big Bang was not an explosion that occurred within space. It was the simultaneous appearance of space itself, along with time and energy at the same moment. Before the Big Bang, there was no space for anything to explode into. There was no time in which a preceding moment could exist. There was no location from which expansion could begin, because location requires space, and space did not yet exist. The universe did not expand outward from a point. Space itself came into being, and has been expanding ever since, carrying everything within it along for the journey. This distinction has an important consequence for one of the most natural questions anyone asks when first confronting cosmology. What existed before the Big Bang? The question feels entirely reasonable. Every event we have ever encountered has a cause that precedes it. Every beginning has something that came before. Asking what preceded the Big Bang seems like the most logical next step after accepting that it happened. But the question contains a hidden assumption that does not apply here. It assumes that time extended backward before the Big Bang, that there was a before to speak of at all. Time, according to our best current understanding, came into existence at the Big Bang, alongside space and energy. There was no previous moment. There was no interval of time during which something else could have been happening. Asking what existed before the Big Bang is, in the precise language of physics, a question without a valid frame of reference. The analogy that captures this most cleanly is geographic rather than temporal. If you stand at the South Pole and face any direction at all, you are facing north. Every direction from the South Pole is north. There is no direction called south from that location because south is defined as toward the pole, and you are already there. Asking which way is south from the South Pole is a grammatically correct question, with no meaningful answer. The question itself assumes a framework that breaks down at that particular point. Asking what came before the Big Bang works the same way. Time, as we understand it, does not extend behind the origin point. The question is grammatically valid and intuitively compelling, but it asks for a direction that does not exist within the structure of reality as physics currently describes it. What physics can speak to is what the very early universe was like, and the evidence for that is extraordinarily detailed. Roughly 380,000 years after the Big Bang, the universe had expanded and cooled enough for a profound transition to occur. Before that moment, the universe was so hot and dense that electrons could not remain bound to atomic nuclei. Every atom that tried to form was immediately torn apart again by the intense radiation flooding the young cosmos. Light could not travel freely because it was constantly being scattered by the dense fog of free electrons filling all of space. Then the temperature dropped to the point where electrons and nuclei could combine and stay combined. Atoms formed throughout the universe in a relatively brief window of time, and with the free electrons now locked into atoms, the fog cleared. Light that had been trapped, scattered endlessly in all directions, was suddenly free to travel in straight lines across space for the first time. That light is still traveling. It has been moving outward for nearly 13.8 billion years. During that journey, the expansion of the universe has stretched its wavelengths from visible light all the way into the microwave range. Today, it fills the entire sky, uniformly arriving from every direction at once, cooled to just under 3 degrees above absolute zero. This is the cosmic microwave background, and it is the oldest light that can ever reach us, a direct photograph of the universe, as it was 380,000 years after it began. But the uniformity of that ancient light conceals a deeper story about what happened in the first fraction of a second, long before that radiation was ever released. In the earliest moments after the Big Bang, in an interval so brief that no unit of time in common use comes close to expressing it, the universe underwent a period of expansion so extreme that it dwarfs every other expansion that has occurred since. During the first roughly 10 to the power of negative 32 seconds, the universe grew by a factor so large that a region smaller than a single proton became a volume many orders of magnitude larger than the entire observable universe is today. This phase is called inflation. Inflation explains several features of the universe that would otherwise be deeply puzzling. It explains why the universe is geometrically flat to such high precision. It explains why the cosmic microwave background looks almost identical in every direction, even between regions that without inflation would never have been close enough to each other to reach thermal equilibrium. It explains why the observable universe is as large as it is despite the relatively young age of the cosmos. But inflation also seeded every structure that has ever existed. Quantum mechanics governs the behavior of matter and energy at the smallest scales, and one of its fundamental features is that perfect stillness is impossible. Even in the lowest energy state, fields fluctuate randomly and unavoidably. During inflation, these quantum fluctuations, tiny random variations in energy density at microscopic scales, were amplified by the extraordinary expansion into density variations spread across vast regions of space. Some regions ended up very slightly denser than average, others very slightly less dense. Those tiny differences in density were the seeds of everything that followed. Over hundreds of millions of years, gravity slowly amplified those differences. The slightly denser regions attracted more matter, which made them denser still, which attracted more matter. The process built the dark matter, halos, the gas clouds, the first stars, the first galaxies, the filaments of the cosmic web, and ultimately the solar system, the Earth, and everything on it. The Milky Way exists where it does because of a quantum fluctuation that occurred in the first 10 to the power of negative 32 seconds of the universe's existence. The same is true of every galaxy Webb has ever photographed. The same is true of every atom in your body. Webb is now testing inflation indirectly by measuring the large-scale structure of the early universe with sufficient precision to distinguish between different theoretical models of how inflation actually proceeded. The specific pattern of galaxy clustering, the statistical distribution of structures at different scales, the detailed features of the cosmic microwave background all carry signatures of what inflation was like. Each observation Webb makes tightens the constraints on those models, ruling out possibilities and narrowing the range of what actually happened in that first unimaginably brief moment. If the position of Earth in the universe was determined by random quantum fluctuations during inflation, does that mean our existence depends on luck at the most fundamental level of reality? Inflation explains the uniformity of the universe, but it also accidentally produces a consequence that many physicists find deeply uncomfortable if inflation happened once. Quantum mechanics makes it almost certain that it happened an infinite number of times, creating an infinite number of other universes permanently beyond our observation forever. The multiverse was not proposed. It arrived uninvited. No physicist sat down and decided that other universes would be an interesting idea worth exploring. The concept did not emerge from speculation or from a desire to expand the boundaries of what science could discuss. It appeared as an unavoidable consequence of theories that were developed for entirely different reasons and that have since been confirmed by extensive observation. If those theories are correct and the evidence for them is substantial, then the existence of other universes follows from the mathematics as directly as any other prediction those theories make. The multiverse is not a story physicists tell. It is a result they have to contend with. The first route to the multiverse runs through inflation. Inflation solved several major problems in cosmology when it was first proposed in the early 1980s, and subsequent observations of the cosmic microwave background have confirmed many of its predictions with remarkable precision. But inflation, once you accept that it occurred, raises an immediate question about how it ended. In inflationary models, the rapid expansion is driven by a field in a particular energy state. When that field transitions to a lower energy state, inflation stops, and the energy stored in the field converts into the hot, dense matter that begins the ordinary expansion of the universe. But quantum mechanics makes that transition probabilistic. Different regions of space do not all make the transition at the same moment. Some regions exit inflation early and become universes like ours, where expansion slows and structures form. Other regions keep inflating. Within those still inflating regions, quantum fluctuations occasionally trigger local exits from inflation, creating new bubble universes. But the space between those bubbles keeps inflating faster than the bubbles expand, so the bubbles never merge and never influence each other. The result, if this picture is correct, is an eternally inflating background in which bubble universes constantly form and drift apart from each other, each one a self-contained cosmos with its own subsequent history, each one permanently beyond the reach of any signal from any other. Our universe would be one such bubble formed when a region of the inflating background happened to undergo the transition that ended inflation locally and allowed matter and structure to develop. Each bubble universe in many versions of this theory can have different values for what physicists call the constants of nature: the strength of gravity, the mass of the electron, the value of the cosmological constant that governs dark energy. These numbers, which in our universe take the precise values that allow atoms, stars, planets, and living things to exist, might be different in each bubble drawn from a vast landscape of possible values. In most combinations, the results are sterile. A universe where gravity is slightly stronger than ours collapses back on itself almost instantly. A universe where the force binding atomic nuclei is slightly weaker never forms elements heavier than hydrogen. A universe where the cosmological constant is even modestly larger than ours expands so rapidly that matter never has time to clump into galaxies. The overwhelming majority of possible universes in this picture are empty, short-lived, or structurally unable to support complexity of any kind. The second route to the multiverse comes from quantum mechanics itself, from the branch of its interpretation known as the many worlds picture, first proposed by Hugh Everett in 1957. In ordinary descriptions of quantum mechanics, a particle exists in a superposition of multiple states simultaneously until it is measured, at which point the superposition collapses and only one outcome is observed. The many worlds interpretation removes the collapse entirely. Instead of the superposition resolving into one outcome, it proposes that every possible outcome occurs with each one becoming real in a separate branch of a continuously branching reality. No branch is destroyed. No outcome is selected over another. Every quantum event that could go multiple ways does go multiple ways, with each way becoming a distinct version of the universe that proceeds forward independently. This is not an analogy or a loose philosophical gloss. It is a literal reading of what the mathematics of quantum mechanics describes when you take the equations seriously without adding any additional rule that causes collapses. The branching is not metaphorical. In the many worlds framework, it is the actual structure of reality. The challenge with both of these multiverse proposals is the same. Other bubble universes lie permanently beyond our cosmic horizon, separated from us by regions of eternally inflating space that no signal could ever cross. Other branches of the quantum wave function are by the structure of the theory inaccessible from any given branch. There is no experiment that allows a direct look into either type of other universe. But permanently unobservable does not necessarily mean permanently untestable. If two bubble universes happen to collide in the distant past, before separating beyond causal contact, that collision might have left a distinctive pattern, a ring-shaped anomaly in the cosmic microwave background. Teams are actively searching for such signatures in the most detailed CMB maps currently available. Webb's precise measurements of large-scale structure also provide data that constrains inflationary models, and different inflationary models make different predictions about the likelihood and character of other bubble universes. The search is indirect, but it is real. If the many worlds interpretation is correct, there is a version of events in which every quantum decision that could have gone differently did go differently somewhere in the branching structure of reality. Every particle that might have taken a different path did take it. Every outcome that quantum mechanics assigns a non-zero probability to has occurred in some branch with full physical reality. The universe you experience is one thread in a structure of staggering complexity, and the fact that you find yourself in this particular thread rather than another is not a matter of selection. Every version of you that quantum mechanics permits exists in its own branch, equally convinced of its own solitude. If the many worlds interpretation is correct, there is also a version of you that watched this story all the way to the end. Unfortunately, we have no way of knowing whether that version is in this universe. If the multiverse exists and cannot be directly verified, is it still science, or has it become philosophy? Whether or not the multiverse exists, one fact cannot be denied. This universe, with these exact physical constants, created the conditions for a species of living creatures to sit beneath the sky and begin to understand it. And that leads to what Webb is truly showing us. Pull back from everything, from the galaxies that should not exist, from the cosmic horizon and the expanding bubble of space we can never see beyond, from the invisible scaffolding of dark matter holding every structure together, from the dark energy quietly accelerating the separation of everything from everything else. From the Big Bang that was not an explosion, the inflation that seeded every galaxy from a quantum whisper, and the multiverse that mathematics produces whether we invite it or not. Pull back from all of it, and a single thread runs through every discovery in this story. Every one of those findings, from the first impossible galaxy Webb photographed to the deepest questions about what came before time itself, eventually circles back to the same point. Not to the edge of the cosmos, not to the moment of creation, to here, to the fact that something in the universe is asking these questions at all. Start with the atoms. The hydrogen in your body was produced in the Big Bang. That part of you is 13.8 billion years old, nearly as old as time itself. But hydrogen and helium were essentially all the Big Bang directly produced. Every other element came later, built through processes that required something the young universe did not yet have: stars. Carbon, the element that forms the backbone of every biological molecule in every living thing on Earth, was forged in the cores of stars through a process so improbable that its discovery shocked the physicist who first worked it out. 3 helium nuclei must collide almost simultaneously, an event vanishingly rare unless the energy levels of carbon happen to be tuned in a very specific way. They are. Without that precise resonance, carbon could not accumulate in stellar cores. Without carbon, organic chemistry does not exist. Without organic chemistry, life as we know it does not exist. The oxygen you breathe was forged in the same stellar cores through further fusion reactions in the final stages of massive stars. The calcium in your bones was built in stellar interiors. The iron in your blood was produced in the cores of stars so massive that when they finally exhausted their fuel, they collapsed and exploded as supernovae, scattering everything they had built across the surrounding space over thousands of light years. The molecular cloud that eventually became the Sun, the Earth, and everything on this planet formed from gas that had been enriched by those previous generations of stellar deaths. The atoms in your body passed through at least one stellar interior before the Sun was born. Some of them may have passed through several. This is not a poetic description. It is a precise account of nucleosynthesis, confirmed by spectroscopy, by stellar evolution models, and by the elemental abundances observed in stars at different ages across the galaxy. When you look up at the night sky and see a star, you are looking at a factory that produced the raw material of which you are made. But it goes further than that. The carbon, oxygen, and iron in your body were not placed here passively. They were organized over billions of years of biological evolution into structures of extraordinary complexity. Structures that developed nervous systems. That developed the capacity to model the external world internally. That developed language and mathematics, and the ability to encode observations into abstract frameworks that predict future observations with extraordinary accuracy. In other words, the universe did not simply produce matter. It produced matter that eventually organized itself into a form capable of turning around and asking where it came from. We are not observers standing outside the universe looking in through a window. We are part of the universe, assembled from its oldest material, using processes that emerged from its history, attempting to reconstruct the story of our own origin. When Webb photographs a galaxy that formed 13 billion years ago, it is not a machine looking at something foreign. It is the universe examining its own past through instruments built from atoms that were once inside stars. This makes the silence even harder to ignore. Webb has now mapped a cosmos of staggering scale and richness. Hundreds of billions of galaxies within the observable universe alone, each galaxy containing hundreds of billions of stars on average. Many of those stars almost certainly hosting planetary systems. The universe is 13.8 billion years old, which means there has been time in many of those systems for processes like the ones that produced life on Earth to occur, complete their work, and produce civilizations, billions of visas. Years more advanced than ours. And yet, no signal, no artifact, no structured transmission detected in any direction across any wavelength, across any timescale of observation. The universe that Webb reveals, teeming with structure and potential, is wrapped in complete silence. This is the Fermi paradox, and Webb has made it sharper, not softer. Every new galaxy Webb finds, every new exoplanet survey that confirms how common planetary systems are. Every detection of organic molecules in distant star-forming regions adds to the inventory of places where life could have arisen. And the silence from all of those places grows more conspicuous with each addition to that inventory. There is no consensus explanation. Perhaps life, while chemically inevitable, faces barriers to complexity that are far rarer than the conditions for its origin. Perhaps civilizations consistently destroy themselves before reaching the stage of interstellar communication. Perhaps the universe is so large that signals from other civilizations have simply not reached us yet, and the silence is a consequence of geometry rather than absence. Perhaps we are for reasons that remain entirely unclear among the first. Whatever the explanation, the silence itself is a data point. And it is a data point that Webb, by revealing just how vast and populated the cosmic stage truly is, has made impossible to overlook. Then there is the question of when. We exist at a specific moment in cosmic history, and that moment turns out to be a peculiar one. The universe is old enough that stars have had time to live and die through multiple generations, enriching the interstellar medium with the heavy elements that complex chemistry requires. It is old enough that galaxies have had time to settle into relatively stable configurations hospitable to long-lived planetary systems. It is old enough for planets like Earth to have formed for life to have emerged, and for that life to have had 4 billion years to develop the capacity for science. But the universe is still young enough that most of the galaxies within our observable region are still visible. Dark energy has not yet pushed them beyond the horizon. The night sky is still full of light from billions of galaxies spread across cosmic time, a record of the universe's history written in photons that have been traveling for billions of years to reach us. That will not always be the case. As dark energy continues driving the expansion, galaxies beyond our local gravitational neighborhood are gradually being carried away. The recession is slow on human timescales but relentless on cosmic ones. Hundreds of billions of years from now, the galaxies we can currently observe will have crossed our cosmic horizon. Their light emitted from that point forward will never reach us. The night sky will go dark except for the few dozen galaxies gravitationally bound to our local group. A civilization that arises, then, will look out into what appears to be an almost empty universe, with no evidence that any of the structure we see today ever existed. They may develop cosmology and conclude with what seems like complete justification that the cosmos contains almost nothing. We live in the window, the specific, finite, unrepeatable window during which the observable universe is simultaneously old enough to have produced us and young enough to still show us where we came from. That window will eventually close. It will not open again. Knowing that we are living in the rarest moment in the history of the universe, the moment capable of observing and understanding it, does that change the way you see the present moment? We are creatures who live less than 100 years on. A small planet around an ordinary star in an ordinary galaxy, in a universe that may be infinite. And we built a machine, placed it 1.5 million kilometers away, cooled it to near absolute zero, just to understand where we came from. No other species we know of has ever done that. That is not smallness. That is the most remarkable thing in all 93 billion light-years that JWST can observe.